In the previous section, we learned about what it means for two vectors to be orthogonal. In this section, we will look at orthogonal sets. And a set is orthogonal if each pair is orthogonal to each other. So in this first example, is this set of vectors orthogonal? I'm going to call this u, v, and w. So I really want to look at u dot v, u dot w, and v dot w. And if all three of those dot products are 0, then this set would be considered orthogonal. So u dot v would be -5 plus 8 minus 3 is 0, check. U dot w would be -3 minus 16 plus 21. This is not 0. So I could stop there and say it's not orthogonal. I'm just going to do the v dot w, which is 15 minus 8 minus 7, which is 0. So since u dot w is not 0, the set is not orthogonal. So theorem 4 just says that if you have an orthogonal set of non-zero vectors, then they will be linearly independent, and thus they will be a basis for the subspace spanned by that set. The way I like to think about this is if I start with two vectors, and then I create another one that's orthogonal to both of them, that adds another dimension. So then if I add another one that's orthogonal to all the three, that would add another dimension. So you're just adding dimensions every time you insert another orthogonal vector. Orthogonal bases are nice because the weights of the linear combination can be computed with dot products instead of solving a linear system of equations. So this theorem tells you that if you have a set of vectors that are u1 through up, and those create an orthogonal basis, then every vector in that span, this y is some vector in the span of all the u's. Instead of solving the system, we normally would put like u1, u2, up, and then augment that with y, and we'd solve to find the weights. When it's orthogonal basis, the weights are this formula. In exercise 2, we first want to show that this set is an orthogonal basis for R3, and then we're going to express x as a linear combination using that theorem 5. So to show that this is an orthogonal basis, I need to just show that they are all orthogonal to each other. So I'm going to call this u1, u2, and u3. So if I look at u1 dot u2, u1 dot u3, and u2 dot u3. u1 dot u2 is -1 plus 0 plus 1, that's 0, check. u1 dot u3 is 2 plus 0 minus 2, which is 0, check. And then u2 and u3 is -2 plus 4 minus 2, which is 0. So it is an orthogonal basis because they are all orthogonal to each other, and it is an orthogonal basis for R3 because I have the right number of vectors. I have 3 vectors. So now I want to express the vector 8, -4, -3 as some number times the first basis element plus some number times the second basis element plus some number times the third. Again, the old way was to augment this into a system and row reduce and solve. So I'm just going to apply the weights from theorem 5. So this is C1, C2, C3. So C1 is equal to y dot u1 over u1 dot u1. So y, this is my y, and this is my u1. So I have 8 plus 0 minus 3 over u dotted with itself, so that's 1 plus 0 plus 1. C2 is y dot u2 over u2 dot u2. I get -8 minus 16, and C3, u3 dot y or x is 16 minus 4 plus 6 over 4 plus 1 plus 4. simplifying, I have 2.5, and this one would be negative 1.5, and this one is 2. So my weights would be 2.5, negative 1.5, and 2. So I like to think of orthogonal projections as shadows. And so I'm just going to think about like the sun being up here, and the shadow that would be produced by this vector y would be right here. There are things called oblique projections. So if you move the sun over here, the oblique projection wouldn't be shorter. If you move the sun to this side, then the oblique projection would be longer. We will only do orthogonal projections. There are two ways we talk about orthogonal projections. One is projecting onto a line, and the other is onto a space. So we'll first think about projecting onto a line. So that's why this is an L, as a line. I like to think of this as the projection of y onto u. The reason I like this is because it's telling you that y is being projected onto a vector u. So that means that the answer should be a scalar of the vector u, which is what we have. So this is a scalar times the vector u. So in this picture, we have this plane, this w, and then y is standing out. And if we have the orthogonal projection, we call it the y hat. Notice here, this is a projection onto the space, not onto the vector. And then they also talk about the component of y orthogonal to u. So that's this part right here. So notice this vector z, those two are the same, just different places in space. So when it asks for the component, it is that difference, that line that draws down to the plane. So let's compute in exercise 3 the orthogonal projection of 1, 7. So I'm going to say projection of y onto u. So I know that the projection, the y hat, has to be some multiple of u, and it's y dot u over u dot u. So if I take the dot product between y and u, I get negative 4 plus 14 over u dotted with itself, 16 plus 4 times negative 4, 2. Just simplifying, I get 10 over 20, so that's 1/2. I get negative 2, 1. So the orthogonal projection of 1, 7 onto the line negative 4, 2 is negative 2, 1. It says also find the component. The component is the y minus the y hat, and the original y is 1, 7. Minus the projection, which is negative 2, 1. And I get 1 minus negative 2, which is 3. And then 7 minus 1 is 6. So we just talked about orthogonal sets. Now we're going to look at orthonormal sets. So orthonormal sets are orthogonal, and the length of each vector is 1. So it has the ortho comes from making it be orthogonal, and normal making it have length 1. So orthonormal, you can have an orthonormal set, and you can have an orthonormal basis. So the only difference is the orthonormal basis has the right number of vectors that's needed for that subspace. Exercise 4 asks us to determine if this set is orthonormal. So first thing we want to make sure is, are they orthogonal to each other? Taking the dot product between the two, I get negative 2/9 plus 2/9 plus 0. That is 0. So the set is orthogonal. Now I need to make sure that their lengths are both 1, and it says if they're not, I want to normalize it. So let's look at the length of v1. That is the square root of v1 dotted with itself. So this is the square root of 4/9 plus 1/9 plus 4/9, which is square root of 1 or 1. So that one does have length 1. The norm of v2 is square root of v2 dot v2. So the square root of 1/9 plus 4/9 plus 0. which is the square root of 5/9, or square root of 5 over 3. That is not equal to 1, so I need to normalize this vector, and to normalize it I want to divide by its norm. So normalize v2 by taking 1 over the norm of v2 times v2. So this is 3 over square root of 5 times 1/3, 2/3, and 0. So I get 1 over root 5, 2 over root 5, and 0. So if I replace that second vector, this is an orthonormal set. It is not an orthonormal basis for R3 because there's only 2 vectors, but it is a basis for some subspace, a 2-dimensional subspace. A matrix that has orthonormal columns is usually called U, and we know that U transpose times U is equal to the identity. U is used for a word called unitary, which happens to be orthogonal in the complex realm. Again, we won't look at that, but that's where the U comes from. Theorem 7 tells us several different things. This first one we'll investigate a little bit more. It just says that if you multiply a vector by a unitary matrix, or a matrix with orthonormal columns, then it does not change the length of that vector. Exercise 5 has you kind of do this. So let's use the matrix U from the previous example. So we found 2 orthonormal vectors, -2/3, 1/3, 1/3, and then 1 over root 5, 2 over root 5, and 0. So that's my U. And let's let x equal the -2, 3. And I want to calculate both the norm of x and the norm of ux. Let's start with doing the norm of x, which is the square root of x dot x. So that's the square root of 4 plus 9, or square root of 13. Now let's calculate u times x. So keep in mind that u is a 3/2 and x is a 2/1, so my outcome will be a 3/1. And remember, when I multiply, I'm going the rows and columns. So I have 4/3 plus 3 over root 5, and then -2/3 plus 6 over root 5, and then I have -4 over 3. Now let's calculate the norm of ux. So that's the square root of the dot product with itself. So this is going to be 4/3 plus 3 over root 5 squared plus -2 over 3 plus 6 over root 5 squared plus -4/3 squared. So square root of, FOIL this out, I get 16/9 plus 9 over 5 plus 2 times 12 over 3 root 5 plus 4/9 plus 36 over 5 minus 2 times 12 over 3 root 5 plus 16 over 9. These two are the same, so they'll add together to be 0. Combining all the 9ths together and then all the 5ths together, I get 16, 32, 36 over 9 plus 45 over 9, or 5. So this is square root of 4 plus 9, which is square root of 13. So I just wanted to verify these two are the same. So this by no means is a proof that this is true, but it does demonstrate this right here, so that the length didn't change when you multiplied by a unitary matrix.